starting chapter 11. And we are talking about the many forms of energy. We are moving away from Newtonian mechanics. And what we mean when we say Newtonian mechanics in the physics sense is we are moving away from forces and velocity and acceleration, and really Newtonian is we're dealing with forces, and we're moving away from forces. We're still going to deal with velocity a little bit, but we're talking about it in the forms of energy. So when we talk about energy, real quick, when you're going through the notes here, how many different types of energy can you list? Take a second, write them down, say them out loud when you're writing the notes. How many different types of energy can you list? Well, we have potential, we have kinetic, we have thermal, we have nuclear, we have chemical, we have stored, we have elastic. Right there, I think I just gave 7 different types of energy. So those are all the possible different types of energy that we can talk about from a physics standpoint. What we are really going to focus on, though, in chapter 11 is kinetic and potential, and in chapter 12 we will talk about thermal energy, so we will kind of start talking about heat. But from a kinetic and potential standpoint, kinetic energy means we are moving. If you go to a Mayo Clinic and you see a kinesiologist, most likely that is an individual or a doctor, you have an issue with your joints or your muscles. You have an issue getting around, so he's going to study you. So kinetic energy is energy in motion. When we study kinetic energy, Ke is equal to 1/2 mv squared, or work is equal to our change in kinetic energy. 1/2 mv squared, m being mass, v being velocity. Stored energy can happen in a bunch of ways. So stored energy could be the stored chemical energy in a battery. It could be a rock on a cliff. It could be gas in an engine. Those are things that are going to be used or possibly can be harvested. And when we talk about stored energy, we are going to talk about potential energy, PE. So kinetic was Ke, potential is PE. What is potential energy? It's work done by gravity. So if we go back to that last example, that is the rock sitting on the edge of the cliff. If that rock falls off the cliff, all of a sudden it has a lot of energy. Where's it getting that energy? From gravity. Now it's due relative to our position to Earth, and it's a reference level. You can have the height at which an object has risen. You can have different types of potential energy. For example, if you are thinking in a room, the difference between the ceiling and the floor would be one reference level. Maybe the ceiling and a table would be another reference level. The ceiling and a chair would be a different reference level. If you're going to measure the height and the between those two distances, it's going to vary, and so would your potential energy. So the equation for potential energy, PE equals mgh. M being mass, g being gravity, and h being the height of the object. How far off the ground of relative distance is it? Obviously our mass is in kilograms, our gravity is in meters per second, 9.8, and our height of the object is in meters. Now, when we talk about potential energy and kinetic energy, the two are linked together. Think of a roller coaster. What's the very first thing when the ride starts that you do? You go up the tow hill. Well, what are you doing? You are climbing the hill. You are gaining potential energy. What happens the second you get to the top of the hill? The roller coaster goes down and you start your motion. That potential energy, therefore, is then converted into kinetic energy. So the two are in harmonious, they are synced together. And the system must remain constant. Once you lose in potential, you gain in kinetic. Or likewise, if kinetic is increasing, if I throw a rock off the cliff, its kinetic's going to increase, but as it gets closer to the ground, its potential energy is going to decrease. So kinetic energy and potential energy are always linked together. So what if we take a real life problem with potential and kinetic energy and give it a shot here? So, our example problem. You lift a 7.3 kilogram bowling ball, which would be a 15-pound bowling ball, from the storage rack and hold it up to your shoulder. The storage rack is 0.61 meters above the floor, and your shoulder is 0.112 meters above the floor. Question A. When the ball is at your shoulder, what is the ball's potential energy relative to the floor? Well, we are going to solve for potential energy. Potential energy is equal to mass times gravity times height. We go ahead and we plug things in. We know the mass of the bowling ball is 7.30. We know the gravity is 9.8. Lastly, it's asking what is the bowling ball's potential energy to the floor? Well, your shoulder to the floor in the problem is 1.12 meters. So we're going to take 7.3 times 9.8 times 1.12 with 3 sig figs because gravity is a constant. We don't use constants. 80.1 joules. The unit for energy is joules. Question B. When the ball is at your shoulder, what is the ball's potential energy relative to the rack? Well, potential energy, again, M times G times H. Let's go ahead and plug it in. 7.30 is our mass. Our gravity is 9.8. But now our height is the height relative to the rack. So now we have to compare the distance between the top of our shoulder and the rack. So we know our top of our shoulder is 1.12. We know the rack is at 0.61. Subtract them, and we end up getting 0.51 meters. You take 7.3 times 9.8 times 0.51, and you end up with 36.5 joules. Question C. How much work is done by gravity as you lifted the ball from the rack to shoulder level? Well, work, this goes back to chapter 10. Work is equal to force times distance. The force we are applying on the ball is really the weight of the ball. So we are going to take mass times gravity. We know the ball's mass is 7.30. We know its gravity is 9.8. That helps us figure out the force of the ball. And again, the distance, well, if we're lifting it from the rack to our shoulder, we figure that out, that distance in question B, that's 0.51. 7.3 times 9.8 times 0.51 is what we just did, and they are the same. And they should be the same because if you remember from the first slide, kinetic energy is equal to a change in work. Well, if we gained potential energy, we had to lift it there, and therefore it gained that kinetic energy sooner or later. So that's kind of how we're going to use potential and kinetic energy. Very simple equations, very simple problems on Monday when we talk about that. So elastic potential energy. What is elastic potential energy? Well, that is stored energy. Well, where does the elasticity come from? Well, it's anything that can really bend or be springy. So you're talking about energy stored in a rubber band, a slingshot, a trampoline, a pogo stick when the object bends. So example, a pole vault. The pole is made from fiberglass. It's bending. It increases energy created by the vaulter. That's how it helps flex them and get them over the pole. Mass also has potential energy, and that is highlighted by Einstein's equation E equals mc squared. It's not a very widely used equation. It's popular, but in the realm of physics, when we talk about energy, it's not widely used. It's just more popular. So E equals mc squared. So the three types of energy, the two types of energy that we really focus on: kinetic, 1/2 mv squared, and potential is equal to mgh. And those are the two types of energy that we'll focus on in section 11.1.